is coming the first, I think it will be recorded to your drive. So let me know if it is in your drive, and then please share the files. Not share. Please make me as a collaborator. I will remind you later, Jason. Okay. Okay.
Professor,
Now,
should I just leave the classroom and come back again? Would you be the
no, no, no. If you
okay?
leave the classroom, the Google Meet will be end.
Oh, okay, 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 okay,
Okay. So that's okay. You can
okay,
just
okay,
check the drive later, and then please make me as the collaborators. I
okay,
will email you later, okay, to remind
okay,
you.
okay.
Okay, maybe we can start 9/11. Um, so we can start with writing the what is the butane? Okay, so butane is this, right? 4, 10, 10. Yeah, right. It's H10. Sorry. Converted. Blah blah. Okay. Uh, this is convert to isobutane. So let me write isobutane as this. Then it converted, 40% conversion achieved. I think the first one that I need to write is maybe taking 1 mole basis. Okay, and then maybe I can write the diagram. We'll be having a heat transfer here, and then this is going to be the feed stream, and this will be the output. It will be 93 mole percent of butane. So I will write 93%. From 1 mole will be 0.93. That will be our mole for the butane. And okay, and then 5% isobutane from here. Okay, right? The feed to the reactor contains 93, 5%, and 2% of chloride, 2% of chloric acid, 002 HCl. Okay, I think the HCl is not reacting to anything, so I will just leave the same HCl. And the difference will be, um, let me write this as N for this butane. This is out, and this is for isobutane. Okay. So you need to first to check these two. Okay. So how to check the mole? Oh, I forgot to write. 40% conversion of and butane, right? Meaning the butane will be converted 0.4 times. Okay, so we can write the N for the N butane. This will be 0.93. Okay, that is the very beginning. The mole will be multiplied with this, right? Because the 0.4 is converted, right? Uh, it will be what, 0.6 in my calculation. It's around 56 mole. And then the isobutane, this will be 0.05. This is 0.4 multiply with 0. This. So this is the conversion. So it's converted to isobutane, right? So we'll get 0.42 mole. Okay. And then the question is asking the extent of reactions. So actually, the question A, B, C, D is step by step on how you find at the end of the day how you find uh, how to determine the heat of this isomer reactions. Okay? The heat of reactions. So the extent of reactions you get. This is the N-butane mole in minus mole out. Oh, right. Out minus in, sorry. And then mole for the stoichiometric part. And because the stoichiometric part, there's nothing wrong and there's nothing in this reaction. It's just as it is. It's only 1 mole, so it's only 1. And we can write this absolute value. Out is 0.56 minus 0.93. Absolute value divided by 1. This will be 0.37 mole. Okay, that's our A. And B is, what is B? Calculate the delta HR. Yeah, you taking the reference. Okay, so reference, taking taking these two isobutane at 25 degrees C. Okay, it's a substance. Oh, I think I can also maybe share maybe 1 or 2 links that I found on YouTube, and I think that is pretty useful, especially for taking the table and making uh, the the mole and enthalpy as which one having the uh, reference and which one is not. I will share later. But let me write all this substance here. We only have 2 substance, right? The N-butane and isobutane. Mm, oh, I think number C, we can do number C first instead of B. I think because we can look for the uh, calculate the required rate of heat. Oh, no. Let's just state number B first. Okay, now this will be N and H. Okay, let's look at the substance. The substance on the beginning is taking, if it is 1 mole basis, if it is taking 1 mole basis here, as you may see from the conversions, it has 0.6 and 0.4. Okay, so instead of taking the mole at it is, I will taking the basis mole and then taking the conversion. So this will be H1. This is also H1. This is H2, and nothing here. Okay, actually, number B, you need to calculate the standard heat. I forgot to write that. Sorry. Calculate standard heat is delta H. Write delta H. Isomerization reactions. What you can do to find the isomerizations. So it is actually using the heat of formations. Okay, heat of formations, you can take that on table B1. So actually, I will write the notes here. You can take delta HR as your general standard enthalpy. Okay, but delta HR is actually you can take this heat of reactions in terms of delta HF, in which this means that to form that 1 mole of that substance, you need some energy, and that is this specific enthalpy for formations. You can also have the combustions, right? If you have combustible materials, and also uh, yeah, at least these two, okay, in general. Let me erase this, and you can take that delta HF on table B1 and look for the isobutane and N-butane. So this will be equal with isobutane minus the N-butane. And check the table B1, and actually you get the delta HF is around, I think not really that exact number, but it's around this 9.8. Oh, I think minus, sorry, minus. Okay, you get this, okay, for the delta. And then this is, you can use it to multiply with the extent of reaction later. Multiply with this, and then combine with the table. Okay, combine with the table. So you have two major calculations. So first, you get the calculation for enthalpy from the table, and also enthalpy from the table B1. Okay, and it's mostly it's frequently happen. If you check your exercise, I think in other answer, in other questions, there will be similar approach, that you will have the table, and then you will have also another heat of reaction that you need to plus with this table. Okay, when you need to find the heat transfer. Okay, so from here, the H1 and H2, this is related to table B2. Okay, because you know that both of them are isothermal. So temperature is let me write isothermal, at T is 149. Right? So because you have reference at 25, use that on the integrations from 25 to 149. Use the CP dt for each isobutane and N-butane. Okay, so use it for finding CP for N-butane and isobutane, and you will get H1 and H2. Right, and then you can calculate the heat transfer, that number C. So number C, the heat transfer is delta H, and this is uh, the extent of reactions. Well, I'm writing upside down. Okay. Wait. I need to check something. Uh, am I missing something? Okay. Hmm. Oh, okay. I think we can just move forward. Okay, I think we can move forward. So this plus the sigma output minus, let me write this, an input. And then you can plug in from here, from the table. This is the output, and this is the input. And using the enthalpy that you get from the table B2, these calculations, you're going to put here all the way, and you get the results for the delta H is some value there. And then it's asking, determine the required heat transfer rate for reactor feed off. So for 325 mole per hour. So we can compute with the uh, compute this. So this will be the flow, the heat transfer flow. Mole per hour, but I think we can convert the hour to this second and convert to kilowatt. You can convert them. Okay. D is use your calculated result to determine heat of isomerization. So this is the delta HR for 149 degrees Celsius. And this is actually the delta H here. Divided by the extent of reactions. Okay. Yeah, let me check. Am I correct? Yeah, I think you need to be carefully look the questions. Sometimes it's a little bit tricky to understand the questions. Yeah, use your calculated result to determine heat of isomerization reaction. So you need to check the delta H for the result that you get from number C. Calculate the required heat transfer. That is heat transfer. This is Q or delta H, and define with the extent of reactions, because it's specifically asking the heat of isomerization. So it's asking the isomerization. So which means it related to the stoichiometric part. The stoichiometric part is related to the extent of reaction. So this means that you need to divide by mole, which mole it is. It's the extent of reactions. Okay, because it's specifically asking isomerizations. Okay. Yeah, a little bit uh, longer than usual. So in chapter 8, you are usually be asking this table and then asking this table B2 on or table B in chapter 7 is the steam, right? But in chapter 9 that you need to use table B1, B2, sometimes B8, sometimes B11 if it is the solutions for if you have thermochemistry problem, you need to check the dilutions, the R, right? If you are having the solution and you know the solutions, you know the mole, and you can use the comparison between the mole and you get the R, you can use it for the table B11, but it's restricted only for I think three substance for sulfate, chloride, and phosphate. I think, yeah. So that is the number 911. Let me check whether we can solve how many questions. Let me check other questions. Hmm. Let me check. Maybe 932 or 945. Hmm. Maybe 945 first. 945. 945. Yeah, it's related to the thermochemistry. Yeah, we can look for oh wait, 945. Let me check 945. Yeah, here. A 2 mole percent sulfuric acid neutralized with 5% of sodium hydroxide in continuous reactors. All reactants enter at 25 degrees Celsius. Standard heat of solutions. Oh, you do have the standard heat solution, delta HS for sodium sulfate is that. And heat capacity of all solution may be taken to be a pure liquid of water. And it's given the informations, the heat capacity. How much heat must be transferred if the product solution emerge at 40 degrees Celsius? And estimate the product solution temperature if the reactor is adiabatic. Okay, so you will need to find the temperature. The final temperature. Okay. Okay. First, we can draw the chart or draw the diagram first. Sulfuric acid, sodium hydroxide. Okay, that two component for the feed stream. Okay, so first is acid and natrium hydroxide. Okay, let me write the informations. 2 mole% of the sulfuric acid, right? And then 5 mole%, or maybe here, 5 mole% of the sodium hydroxide or natrium hydroxide, neutralize. Okay. Now, if we take, if we say we have 2 mole% and 5 mole%, what does it mean? Okay, what does it mean? So if we take the mole is 2 mole% means if we assume this is 2 mole, if we have 2 mole of the acid, then in one whole in the whole component we also we also have the water, right? So that 1 mole will be 49. Okay, if you think this is solutions. Okay, or probably I forgot to write the reactions. Sorry, it's neutralized, right? So this acid plus the natrium hydroxide, this will become. So you need to write the reaction first. Sorry. And then plus the water. And then always, I think, solute solutions. I think we need to look the stoichiometry. This is 2, right? Okay. Okay. Now look here. 5 mole is if you have 5 mole of the sodium hydroxide, this will be having the rest as water, right? So first, this is basis, 1 mole acid. And then by the reactions here, you see that the mole that need to be neutralized for natrium hydroxide is 2 mole. So if we write this into 2 mole of natrium hydroxide, this will be 38 right? 519 multiplied by 2. So yeah, 38. Yeah, 38 water. So we can write, if this is having 1 mole, this is 2 mole, it will be having 90 mole water. This is having 38 mole water at the feed stream. And the result is 1 mole. 1 mole of natrium sulfate. I forget how is the... Oh, number A, how much heat must be transferred if the product solution emerges at T is 40 degrees. So if the T is 40 degree, so the reference state, as it mentions that all reactants enter at the same temperature, 25 degrees C. So first, you can look at this because heat capacity of all solution may be taken to be that of pure liquid water. And how much heat? Okay. So for all the elements, let me write all the elements that are essential in this part. All will be in 25 degrees Celsius. Okay. Now first, look at the acid first. If you look the ratio, water to the acid is 49, right? So the R is 49 divided by 1 is just, let me just write 49 at 25 degrees Celsius. So you will have the result of the enthalpy will be 1 mole and then plus the heat of formations. This is from the acid plus acid liquid plus the delta HS, which is you can get from R equal 49. And then don't forget to add the water, 49 delta H F, and then this is water. You can check the results. And for the natrium hydroxide, the R is 19, same temperature 25. The enthalpy is 2 mole. And then calculate the heat of formations, which you are getting the heat of formations from the table. plus the heat of solution. And you can look at table B11. Check R is equal 19. And then plus 38. This is for the water. Okay. And then you see the natrium sulfate. Check that you have 1 mole. So this is, you get a, let me write here. It's having molecular weight around 142. If it is, if 1 kilomole, you can get the amount, the kilogram.